In this podcast episode, theoretical physicist Sean Carroll discusses the concept of general relativity, black holes, and the potential existence of intelligent alien civilizations. Carroll explains that general relativity is a theory developed by Einstein that combines space and time into a single entity known as spacetime. This theory suggests that gravity is the curvature of spacetime, rather than a force acting upon it. Carroll emphasizes the creative leap required to understand and apply general relativity, highlighting Einstein's brilliance in formulating this groundbreaking theory. Special relativity, developed prior to general relativity, laid the foundation for the idea of spacetime. Carroll explains that special relativity eliminated the concept of an ether and introduced the idea that the speed of light is a maximum. This led to the unification of space and time into spacetime, a concept further developed by mathematician Minkowski. The integration of space and time into a single entity was a profound insight that paved the way for Einstein to formulate general relativity. The conversation delves into the possibility of intelligent alien civilizations and the challenges of detecting them. Carroll discusses the Fermi paradox, which questions why we have not yet observed extraterrestrial civilizations despite the vastness of the universe. He speculates on the potential existence of self-replicating probes sent by advanced alien civilizations to explore the galaxy. Carroll reflects on the complexity of life and the challenges of identifying signs of life on exoplanets. He suggests that the presence of long molecules in an exoplanet's atmosphere could indicate the existence of life. The conversation then shifts to black holes, specifically the regions of spacetime with a point of no return called the event horizon. Carroll explains that once an object crosses the event horizon of a black hole, it cannot escape due to the immense gravitational forces. The object eventually reaches a singularity where it is torn apart by gravitational forces. The concept of Hawking radiation, where black holes emit particles and lose mass over time, is also explored. This radiation raises questions about the fate of information that falls into a black hole, leading to the black hole information loss puzzle. Carroll goes on to discuss the concept of the holographic principle and its implications for our understanding of black holes and the nature of information in the universe. He explains that the holographic principle stems from the idea that black holes have a finite amount of entropy, which is the highest density of information that can be contained in a region of space. This suggests that the information in a black hole is not distributed in the volume inside the black hole, but rather on its two-dimensional event horizon. This concept challenges our traditional understanding of how information is stored in physical systems and raises questions about the nature of space and quantum gravity. The holographic principle has led to the development of theories like the ADS-CFT correspondence, which posits a duality between theories in different dimensions of spacetime. This has sparked interest among theoretical physicists in exploring the relationship between quantum field theory and gravity in a holographic framework. While the holographic principle offers a new perspective on information and spacetime, there are still unanswered questions about how it manifests in physical reality. Carroll and his colleagues have conducted research to test the predictions of the holographic principle against experimental data. By examining the behavior of neutrinos in high-energy environments, they aim to determine if the holographic nature of information storage in black holes has observable effects on particle interactions. The ice cube experiment in Antarctica serves as a detector for high-energy neutrinos, providing a platform to test the predictions derived from the holographic principle. One of the challenges in reconciling quantum field theory with the holographic principle is the discrepancy in the amount of information that can be contained in a given region of space. While quantum field theory suggests a higher density of possible states, holography implies a more limited set of information. This discrepancy can be addressed by considering the overlap of states in a high-dimensional vector space, where the states are not perfectly orthogonal to each other. The holographic principle raises questions about the fundamental nature of time and space. While time is a constant progression in our everyday experience, the flexibility of spacetime in the presence of black holes and quantum mechanics challenges our intuitive understanding of temporal dynamics. The holographic nature of information storage suggests a different way of conceptualizing the relationship between time, space, and quantum phenomena. Carroll emphasizes the importance of intellectual humility in exploring speculative ideas in theoretical physics. While there is ongoing research to test the holographic principle and its implications, there is still much to learn about the fundamental nature of the universe. Surprises and unexpected discoveries may await as physicists continue to push the boundaries of our understanding of space, time, and information. Carroll delves into the concept of dark energy, describing it as a field that permeates everything and is unlike any other field. He explains that dark energy is invisible and helps in working out mathematical equations. He draws a parallel between the discovery of dark energy and the discovery of the planet Neptune, emphasizing the importance of evidence in scientific theories. Regarding dark matter, Carroll explains that it is hypothesized to be a particle that interacts weakly with other particles. He mentions that there is substantial evidence for the existence of dark matter derived from observations of cosmic background radiation and large-scale structures in the universe. He also highlights the difference between dark matter and dark energy, stating that dark matter is lumpy and can be mapped out, while dark energy remains constant and uniformly spread throughout space. Carroll then discusses his attempt to unify dark matter and dark energy in a single theory, which ultimately failed to explain both phenomena satisfactorily. He mentions his research papers on limits on Lorentz and parity-violating modifications of electromagnetism, quintessence, and cosmic speedup due to gravitational physics. He emphasizes the importance of impact over awesomeness in scientific research, acknowledging that not all groundbreaking papers receive immediate recognition. The conversation shifts to quantum mechanics, with Carroll describing it as a comprehensive theory that can explain the behavior of tiny particles and the entire universe. He introduces the concept of the many worlds interpretation of quantum mechanics, which posits that multiple parallel universes exist simultaneously. He explains that in many worlds, the wave function of the universe contains all possible outcomes of quantum events, leading to the existence of multiple parallel realities. Carroll addresses the controversy surrounding the many worlds interpretation, acknowledging that it challenges traditional notions of reality and identity. He defends the theory by highlighting its simplicity and adherence to the Schrödinger equation, which governs quantum mechanical systems. Carroll explains that many worlds offer a deterministic view of the universe, where each moment contains the memory of the entire history of the universe. The discussion then delves into the concept of the Big Bang and the origins of the universe. Carroll admits that the question of why the Big Bang occurred remains a mystery, with no definitive answer in sight. He explores different possibilities, including the emergence of space and time, the existence of a singularity, or a pre-existing state before the Big Bang. He also touches on the idea of the universe as the totality of everything, suggesting that there may be no concept of outside the universe. Carroll delves into the concept of complexity in the universe, emphasizing the emergence of complexity from simple interactions. He discusses how systems evolve from simplicity to complexity, highlighting the role of information in driving this process. He mentions cellular automata as a fascinating example of how complexity can arise from basic rules and interactions. He is particularly interested in understanding the mechanisms behind the emergence of complexity and how it relates to the fundamental laws of physics. The conversation shifts towards artificial intelligence and large language models, with Carroll expressing cautious optimism about the progress in this field. He acknowledges the remarkable advancements in AI, but emphasizes the need for clarity in defining and measuring complexity in these systems. He discusses the different forms of complexity, such as configurational complexity and computational complexity, and explores the challenges in developing a unified understanding of complexity in AI systems. Carroll provides insights into entropy in the universe, highlighting the role of black holes as repositories of immense entropy. He explains how black holes contain a vast amount of entropy, surpassing the entropy of the entire observable universe. He discusses the distribution of entropy across space and the implications of entropy for the evolution of complex systems. He emphasizes the interconnectedness of entropy, complexity, and the arrow of time in shaping the dynamics of the universe. Carroll delves into the stages of complexity in the universe, starting from the early universe's simplicity and low entropy. He discusses how complexity evolves through different stages, including the formation of stars, the origin of life, and the development of cognitive abilities in organisms. He highlights the role of information processing and imagination in driving the emergence of complexity, particularly in human cognition and decision-making processes. The conversation touches upon the controversial topic of panpsychism, the idea that consciousness permeates all matter in the universe. Carroll expresses skepticism towards panpsychism, citing the challenges in reconciling conscious awareness with physical behavior at the atomic and molecular levels. He engages in debates with proponents of panpsychism, such as David Chalmers and Philip Goff, discussing the limitations of physical explanations for subjective experiences and the nature of consciousness. Carroll delves into the age-old debate of dualism versus physicalism when it comes to explaining consciousness. While some argue that the subjective experience of consciousness cannot be captured by physics alone, Carroll takes a physicalist stance, asserting that consciousness can be understood within the framework of the laws of physics without the need for a separate entity like the mind. Carroll distinguishes between illusions, which are perceptions that do not align with reality, and emergent properties, which are real but arise from underlying physical processes. He argues that consciousness, like the hardness of a table, is an emergent property that can be explained within the realm of physics. Carroll discusses Donald Hoffman's theory that the concept of space-time is an illusion and that there is a deeper reality beyond our current understanding. While acknowledging the validity of structural realism, Carroll emphasizes the importance of recognizing different ways of describing the natural world without dismissing them as illusions. Carroll explains his belief in naturalism, the idea that the natural world is all-encompassing, and poetic naturalism, which allows for multiple perspectives and interpretations of reality. He highlights the importance of incorporating normative and prescriptive language in addition to descriptive scientific vocabulary when discussing the universe. Carroll expresses his admiration for general relativity, calling it the most beautiful theory ever. He finds satisfaction in teaching the subject due to its clear assumptions and far-reaching implications, culminating in Einstein's equation that transcends the limitations of human knowledge. Carroll shares insights into his process of preparing for interviews and writing popular science books. He discusses the balance between rigor and accessibility, aiming to make complex topics understandable without sacrificing depth. Despite facing challenges like getting lost in rabbit holes and managing time constraints, he remains dedicated to engaging with a diverse range of subjects. Carroll touches on the Nobel Prize's limitations and controversies, noting instances where deserving individuals like Einstein were overlooked for their groundbreaking contributions to science. He acknowledges the human element in scientific endeavors, including collaboration, competition, and the complexities of recognition within the scientific community.